Good. So today, we are continuing with the shear force bending moment, even though today should have been the actual lecture 4. Last time we couldn't finish. So I've decided that let me just continue with the lecture 3. Okay, so last time our focus was calculation of support reactions for determinate beams, and we did a lot of examples. For example, we were able to learn how to the various sign conventions. We also learned how to calculate reactions for various beams. We started with the simply supported beams, right? And we did this example. And as you can see, the solution has been provided. We also did example 3.2. We also did 3.3, 3.4, 3.5, and we also kind of started with cantilever beams. But I remember that one we solved only one example. And so for that reason, I am going to restart the cantilever beam, problem 3.6, and then we continue from there. So right now, last time our sign convention is that if the force is moving upward is positive, downward negative, horizontal force to the left is negative, to the right is positive, clockwise movement is negative, anti-clockwise is positive. And we learned about taking moment, about various reactions. And then based on that one, we were able to do the calculation of the support reactions. So we are going to do the continue with cantilever beams, okay? So with these cantilever beams, today we'll require to do some writing. So I'm sharing my notes. I'm sharing this. In order to be sure that you have seen my screen, I want to do this. Or just to make life easy, I will just make it something small. Can you see my screen? If you can see, you can just say yes, because this is, I've written something. So I've moved from the usual slides. Okay, good. All right. So now that you have seen that I've written James, we can comfortably proceed with our class. So, as I said, today, even though today is lecture 4, it is still lecture 03. Shear forces and bending moments. So essentially, this is kind of extended lecture 3, even though today is supposed to be a lecture 4. So we are continuing with computation of support reactions. And now we are dealing with cantilever beams. Okay? All right. So under the cantilever beams, we have problem 3 point. Problem 3.1, 3.6. We have problem 3.6. All right. So we are going to solve that problem again. Yes, I understand we did that. That's fine. It's not a problem. So this is a problem 3.6. So this one is 90 kilonewton, 135 kilonewton. This is A, B, C. So this is essentially the given question. We are to calculate the reactions. So I'm just going to write here. Let me bring it a little bit down, a little bit down, a little bit down. So this is given. Okay. So let's look at the solution. Okay, here is fine. Let's proceed. So this one, the distance that was given to us from here to here is 3 meters. 3 meters. And so as we have received the given, in the solution, we need to provide the free body diagram. Okay. So I'm going to just copy and paste here. Just copy and paste. So let me move it a little up. So this one is my free body diagram. I'm just going to modify some few things here. Okay. So as we know already, with a free body diagram, we represent the support by their correct reactions. So this is fixed end. So I have vertical, I have horizontal, and I have a moment. So this is a moment. This is at point A. So this is HA, and this is VA. Okay. And this distance are 333. So now, this is now our free body. It's compulsory to draw this as usual, right? So we're going to use our free body now. So what we learned was that when it comes to cantilever, first take moment about the support. Okay, so I'll say taking moment about A. Okay, and you remember our formula? Sum of moments about A is equal to 0. The anti-clockwise is positive. This might be written. So now, as you can see, if we take moment about A, it means the A is our pivot, and the 90 kilonewton will be clockwise moment, 135 will be clockwise moment, and then the horizontal and vertical force at the point is 0, but the moment cannot be 0. Okay, the moment cannot be 0. So in that case, the moment there is MA, okay, is MA, and then we have, that's anti-clockwise, so it's positive, right? It's positive. Then we have the 90 will be clockwise moment, so negative, and then 135 will also be clockwise, and the distance is 6, and this will be 0. So this one will give us MA minus 270 minus 135 times 6 will be 810, will be 0. So what's going on here? MA minus 270. Right, so when we put this together, we're going to have MA minus 1080, and this will give us 0. Okay, so we proceed with just the usual mathematics until we get what we want. So MA here is equal to 1080 kilonewton meter. So remember that it's important to first take moment about the support for cantilever. If you start from there, you will not struggle in your computation. Okay? Now, after we have done that, what do? We take moment at the free end. So taking moment about the free end is C, right? So sum of moment about C is equal to 0. You need to show that anticlockwise is positive. Okay? So in this case, we have the 135 is not a reaction, so it's time a distance of 0. Then we have 90, this will be anticlockwise, a distance of 3. We have VA, that will be clockwise times a distance of 3 plus 3. And then HA will be times 0 because it's along the axis of the beam. And then the MA will also come into the equation. So we proceed by saying 135 times 0. Okay? Then the next one, this minus plus 90, okay? 90 times 3. And then minus VA times 3, times 6, right? Then what again? What again? The moment plus ME and then plus HA times 0. Okay, so let me shift this way a little bit. And this will give us 0. So this, when we multiply this, Labi, what is the problem? Labi, what is your problem? Okay, let me just proceed with the class. All right, so this one will give us 0 plus 90 times 3 will give us is that 1080? 90 times 3. Okay, 90 times 3. 270. This will give us 270 minus 6 VA plus MA plus 0 is equal to 0. So we have 260 minus 6 VA. Do you realize we have already calculated the MA? The answer was 1080 plus 0 is equal to 0. So if we add 260 plus 1080, that will give us, is there anything wrong somewhere? Okay, let me see the message people are sending here. 270. Labi. Please, Labi, if you don't speak, I don't know. What's the problem?
Sir, I'm here. I put it on mute, that's why.
What's the matter?
Sir, the 135 times the 0, I didn't get that one well.
The reaction is at that point, so there's no distance.
Oh, okay.
So put down your questions, eh? In due course, I'll ask for questions, but not now. So now, adding this together, we'll have 1350 minus 6 VA is equal to 0, right? So that negative 6 VA is equal to negative 1350. So that VA is equal to negative 1350 over 6. And VA is going to give us 225 kilonewton. Is that okay? Okay. I'll correct that. So this should be 270. Okay. So as usual, that's what we have done. We know there is a horizontal force, okay? There is one horizontal force. But even this calculation, why don't I move it here so that it become easy to recall with. I'm coming, eh? Okay, so now we have been able to calculate the reaction A and the reaction MA. Now we need the horizontal force. So as you can see, we have only one horizontal force. Okay, so I may even copy this. I may copy it so that we can take it to the other side to work with. Okay. Good. So let's proceed. Now that we have finished with the other, so I'm pasting here for just for convenience so that we look on it to do the rest. So right now, the next thing we have to do is the horizontal reaction. Okay. So horizontal forces. So this one again, sum of forces in the x direction is equal to 0. And we say if it is moving to the right, it's positive. We have only one, right? So that one alone is 0, and that ends it. Then after that, what do? We check. We need to check our computation by using this sum of forces in the y direction is equal to 0. Upward is plus. Okay. So I've brought the diagram here for good reason. So looking at this diagram, the upward force, we have VA minus 90 minus 135. We say this one will give us 0. So the VA is 225 minus 90 minus 135. And this is 0. So once you get 0, it means that your reactions are correct. So in sum, once again, you in cantilever has only one support, so you take reaction at the support. That's the important thing. If you take reaction at the free end first, you have two unknowns, so you have to leave that equation. You go and solve for the other one before you can come. So it is very simple to rather take your first moment at the support, your second moment at the free end, and then subsequently you can do it without any back and forth. Okay? Any question? Any question? Okay. So this diagram is not part. I'm just going to delete it. All right, so then we'll move to the next problem. Move to the next problem. So the next problem is problem 3.7. And next problem is problem 3.7. So given. So this one, and then we have this one is 25 kilonewton per meter. This is 75 kilonewton. This is point A, B, C, and D. Okay, let me move it up. Okay, so now let me put the distances. So this one is 6 meters. This is 6 meters. And this is also 6 meters. All right, so we need to provide our solution by starting with a free body diagram. Okay, so I'm copying this. Copy. I'm bringing it here just to modify something small. Good. So as you can see here, you see that it's the same diagram. The only thing that need to change is the support converted to their appropriate reactions. So this one, we have vertical, we have horizontal, and then we have a moment. So this moment here is called MA, HA, and then this one is VA. All right, so if you remember, there was a certain principle I taught you that as soon as you have a distributed load, the first thing you should remember doing is convert the distributed load into equivalent concentrated load and use it for your calculation. So in that regard, this is UDL, right? So I'm converting it into equivalent UDL, and I told you this is UDL. I don't like this color. Okay, so I'm doing the conversion. So this is UDL. So this is how we convert it. The omega 25 times the span covered by the UDL, which is 6. After that, we need to indicate this distance. This is half, 3 meters. 3 meters. Okay, so once you have done this, remember I said this should be in pencil. That's why I've used a different color. You are doing this just to help you solve the problem easily. So this particular one, we are now having 2-point loads. Okay, we have the ECL and then the 75-point load that was given to us. Okay, so now let me shift it a little up as we focus on the solution only. So this time around, we are still going to taking moment. Now let me indicate that this is a free body. It's important to do that. This is free body diagram. Okay, so now taking moment about A, because that's where the fixed support is, so that I will say sum of moment about A is equal to 0 and anti-clockwise is positive. If this equation is missing, I'll give you a very nice 0. Okay, so this time around we have added support. I told you that as for the support reaction, we shouldn't worry about them. If I take moment at A, all the support reaction there, if it is no moment, it will have 0 distance. So we just ignore them. Even if you write VA times 0, it's still 0. HA times 0 is still 0. But the moment cannot be 0. So it will remain the moment MA. Remember that this moment here, if all the reactions, usually we are guessing their direction. So it's important to be consistent with positive directions. If you put a clockwise moment there, you must remember that during your calculation, you must use clockwise. Okay? It doesn't matter the direction that you put. After the calculation, it will tell you the correct direction. So it's not an issue. It's kind of a guess direction, okay, which everybody can do. Is that okay? So moment at A is anti-clockwise, so this is positive. Then we have 75 times a distance of what? 6. That's what? Clockwise. Then now the ECL is what? 25 times 6. This force is also clockwise. But the distance will now be 3 plus 6 plus 6. Is that right? Okay. So now, let me now move into action. So we have minus 75 times what? 6. Then minus 25 times 6, which is the force. Then the distance, 6 plus 6 plus 3, that will be 15, right? That will be 15. Then I said, you must put this whole thing into a square bracket. You put it into a square bracket. Then what again? That's all. We equate it to 0. So now we have MA minus 450 minus 2250 will be equal to 0. Okay, so let me move up now. So when we put this together, we'll get MA minus 2700 is equal to 0. So that MA is equal to 2700 kilonewton meter. So if the assumed direction is not correct, my answer would have been negative. That's a simple thing. If your answer is negative, then it's telling you your assumed direction is not correct. But don't worry, just proceed with the calculation like that. Don't go and change anything. Okay? Don't go and change anything, proceed with the calculation. So now, the other part now is taking moment, About the free end, this time is D, right? So sum of moment about D is equal to 0. Anti-clockwise moment is positive. Okay, I guess I have something here. Yeah, okay. So let me, just for all of us to see it again, okay? So this particular problem, you notice that we are now, our pivot is here, right? At D. So this one will be anti-clockwise. That will be 3 meters. This 175 will be anti-clockwise. That will be times the distance of 12. And then the VA will be clockwise times the distance of 6 plus 6 plus 6. And then the HA will be times 0 because it's along the axis of the beam. And then the MA will also come. Okay? The MA will also come. So now that we have seen it, I'm just going to write all that we have just said here. Okay? So I'm going to write everything. So we first of all have the, okay. If I copy this, there will be no issues. So it's fine. Just to make sure nobody get lost. Okay, so I just want to bring it by the side here. Okay. I don't know what has appeared here like a camera. Uh, okay, maybe I'll find means of, okay, it's here. Good. So this time around, as you can see the diagram, I'm going to write them as we discussed there. I'm going to have 25 times 6 and multiply by 3 in a square bracket. That will be anti-clockwise, so it's positive. Okay? Then we have plus 75 times 12 will also be anti-clockwise. Then we have the moment is anti-clockwise. We have MA, or if you like, we have minus, we have VA times 18. We have MA, we have plus HA. I think that this thing is going to distract me. Good. So let it be in the corner there. So plus MA plus HA times 0 is equal to 0. Okay? So when we multiply this one, we'll get 450. Multiply this one, we'll get 900. This one will get 18 VA. Do you remember the value for MA? MA is 2700. 0 equals 0. So when we add all the like terms, we'll get 4050 minus 18 VA. So this diagram too is all about distraction. It's all about distraction, distracting me left, right, center. That's why I didn't even want to bring it at all. Okay, it's fine. So let's proceed. So this is equal to 0. Now we're going to have negative 18 VA is equal to what? 40, 50. So VA, this will be negative, will be equal to negative 40, 50 over negative 18. So that VA is going to give us, hey, that's interesting, 225 kilonewton. You must note the units very well. Is that okay? If you don't use the appropriate units, it's not right. We have horizontal forces. There's a horizontal reaction here, okay? So we need to consider the horizontal forces. So horizontal forces. We have sum of forces in the x direction should be 0, and then going to the right is positive. So how many? We have only one. We have only one. HE is going to the right, so it's positive. Then that's all. We equate it to 0, and that be it. As I kept emphasizing, if it's an exam, let's say if I give this one 5 marks, this horizontal will also get 5 marks. Because it should be noted that it's not every time that the horizontal force will be 0, that you say that is 0, 0, 0. No. Okay, so now we apply the checks. Sum of forces in the y direction is 0, upward is positive. Okay, so now we have VA, we have 75, we have 25, times 6. That's all. Should give us 0. So that 225 minus 75 minus 150. When we do this, we'll get 0. So check. Okay? Once you get 0, it means that you are right. And as I did indicated in a previous class, you must always get 0. If you get any figure other than 0, it means that your reactions are not correct. And you need to quickly go through, okay? Cross-check and see where the mistakes are for your corrections to be done, okay? Any question here? Any question? Any question? Okay. So since you don't have any question, at this point, we have dealt with all the kinds of loads, point load, whatever, So it's important to know how we go around it. Emmanuel. Once I mention your name, I have given you opportunity to unmute, so you have to follow suit, right?
Okay, sir. Sir.
Yes.
Sir, please, good morning.
Good morning.
Sir, please, I wanted to ask about Please, I wanted to ask about the beams.
Ask
Hello,
your
sir.
question. Ask your question. Because what you are saying is not a question.
Sir, please, I wanted to know if we could get some pictures of the beams as in the real life pictures.
Don't you know a beam?
Sir, please, I know a beam.
So what pictures are you referring to? I should go and snap pictures and come and paste it on the slide here.
Sir, please, I wanted to ask about the pictures of the type of beams.
So, once I've taught you, it's your duty to go and look for the real life pictures, because I use a lot of structures on campus to cite example of the various type of beams. So you,
Okay, sir.
as a student now, have to go and be checking the structures and try to identify them. Because the farthest I could go is to illustrate, showing example of this type of beam on campus, using structures on campus. So your duty is to go back to these structures I was referring to and check them.
Okay,
The
sir.
lecturer cannot do all the work. After giving example, I'm going to take pictures and share. That is beyond the lecturer, right?
Okay, sir.
Okay. So after
Thank you
class,
very
go
much.
and check the various examples I've given. Go and check and see whether you
Okay,
can
sir.
identify them. Okay, that's how we
Okay,
learn.
sir.
All right.
Thank you very much.
Okay. So you can lower your hand now, Ima. So now, I think that is enough for cantilevers. Okay, that's enough for cantilevers. So the same principle will be adopted anytime you are dealing with cantilever beam. Okay, so now we are moving to another kind of beams, which we call beams with overhang. I believe that you remember we have dealt with different types of beams, and that we have also dealt with beams with overhangs. So we're going to take a problem. So this one, we take problem 3.8. So this is the given information. So with the beams with overhang, I'm going to provide a question. Okay, so this particular, we have a load here. We have a support here. We have a load here. We have a support here. We have a load here. So this side no more necessary. So we have 55. Kilonewton. We have 110 kilonewton. 110 kilonewton. 55 kilonewton. So let me try to put the dimensions. Everywhere is 3 meters. 3 meters, 3 meters, 3 meters, 3 meters, 3 meters. So this is A, this is B, C, D, E, okay, F. If I can even bring this B at the top here, I can bring it down. Call this one D. Okay. So this is the beam with overhang. I think my diagram is a bit disproportionate. Okay. So easy. So yeah. Let me clean here small. I don't want to have a disproportionate diagram. F. Okay. So this is a beam with overhang. So you can see that this beam has overhangs on two sides. What type of support is at B? I need an answer. What type of support is at B? What type of support is at B? You can put the answer in the message box. Don't worry. What type of support is at B? Okay, good. At least all of you who have given answer, you've got it right. So that is a hinge support indeed. What about the support at E? What support is at E? Okay, well, all right, good to hear. That's a ruler support. Okay, so I'm just trying to now provide the appropriate reactions to complete my free body diagram. So as we know already, this side, you see that I cannot put the reaction on the beam. I will not see it. That's why I've dropped it a little bit so that this is HB. Okay, this is just a common sense approach. This is VB. And this side, we have a support here. And this one is VE. Okay, VE. All right. So what I'm saying is that you have a beam like this. You can't put the reaction inside the beam like this. It doesn't make sense. That's why I've dropped it a little bit. So nobody should ask me why I've dropped it. Okay. All right. So good to have all these answers from you, active class. So now, once I've drawn my free body, I will move up then. Okay. Now, I need to indicate that this is my free body diagram. It's important to indicate it too. You must write the name that this is a free body diagram. So now we'll take moment. Remember that, always remember, it's very simple to take moment at support. It's always simple like that. Okay? So I'll still take moment about my support. I'll take it at, first of all, B. You can take it at left first, it doesn't matter. Sum of moment about B is equal to 0. Anti-clockwise moment is positive. Now watch here. Now that we have taken moment about B, this is now our pivot. Okay? Looking at like drawing a circle as we have learned, we'll start with the extreme left. The first 55 here will go like this. That's anti-clockwise, isn't it? And then the 110 relative to the B will go like this. That's clockwise, isn't it? And then 110 here to also go like this. That's also clockwise. And the distance is what? 6. The 110 here, the distance is 3. And then 55 here, the anti-clockwise moment. This one, the distance is also 3. Then we have the VE. Okay? VE will go like this. So about B, so we calculate from E all the way to B. That's 3 plus 3 plus 3, 9. Okay? Then the 55 at the last end here will be clockwise. We calculate 3 plus 3 plus 3 plus 3 all the way to the B. All the time, we are taking moment about B. So your distance must always be calculated up to where you are taking the moment. Is that okay? Any question? Any question? Okay. So I think that everything is clear now. So let's see how we're going to have. I'm left with this mark here. We're going to have, first of all, you start from the extreme end of the beam so that you don't miss any of the load. So we have 55 times a distance of 3. And as we saw, this will be anti-clockwise. Then minus 110 times what? 2. Times also 3 up to the B. Then we have 110 times 6. Then we have VA, VE times a distance of what? 9. Then we have minus 55 times the distance 12 plus HB times 0. This will give us 0. Okay, this will now give us 0. This will give us 0. Okay, so then we proceed with the computation. 55 times 3 will give us 165 minus, this will give us 330 minus, this will give us 660. This one will give us 9 VE. 55 times 12 will give us 660. This will give us 0. We equate to 0. So when we put all this together, going to have -4, -1485 plus 9 VE is equal to 0. Okay, so 9 VE is equal to 1485. So that the VE is equal to 1485 divided by 9. Okay. So that is going to give us VE is equal to 165 kilonewton. Okay, so that's the first part. Good. So let me look at taking moment about point E, right? Because that's where our reaction is. Taking moment about E. So sum of moments about E is equal to 0. Anti-clockwise is positive. Okay. Good. Somebody calculated it. All right. So let me just go back here and copy the diagram. Okay. So that we can use it subsequently. Okay. I'm just going to paste it a little bit down here so that we'll use it to learn. Good. Okay. So as you can see, um, once again, we are taking moment about what? E. Is that right? So the E now, okay, I could have just ignored this triangle. I could have said this is now our pivot. So I'll consider to my right because some of the forces are there. So this one about the pivot will be clockwise. Then the 110 about the pivot will be anti-clockwise. 110 anti-clockwise. Remember the distance is from here to the pivot, 6. This one is 3. Then our VB, right? That will be clockwise. The distance will be what? From there to all the way to the E, that will be 9. And then I have this one, and this one, the distance from there, from the force to the pivot will be 12. Then the horizontal force will still be 0 because it's along the axis of the beam. Okay. All right. So with that understanding, we can now simply write we have 55 times a distance of 3, and that is clockwise. Okay. Then we have plus 110 times 3 anti-clockwise. We have plus 110 times 6. Okay. Then we have minus VE times a distance of 9. Then we have plus HE times 0. Okay. We have plus the 55 there, 55 times 12. And this should give us 0. Is that okay? So now, I hope that you are actually following and you are also doing your own calculation behind the scene. That's how we learn. Okay? So essentially, this one will give us negative 165 plus, and this one will give us 330 plus. This one will give us 660. This will give us 9 VE plus 0 plus 660 0. Okay, so now when we put all this together, we will get 1485 minus 9 VE is equal to 0. So that negative 9 VE is equal to 0. Okay. Negative 1485. So that the VE is equal to negative 1485 divided by negative 9. So that VE is equal to, when we calculate that, 8. Okay. That will be VB, right? It's not VE. This one is VB, okay? This is VB. I don't know why I've used the E all along. So VB. This is also HB. I don't know where these mistakes are coming from. HB. B, 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 B. And this one will give us 165 kilonewton. Okay. So now that we are through with that, okay, Richard Mason has also got 165. That's good. So now that we have got that, we'll proceed to do horizontal forces. Okay, so we do it. There is a horizontal force, so we cannot skip that. So horizontal forces. So we have sum of forces in the x direction is equal to 0. To the right is positive. We have HA. This is the only horizontal force we have, so it means it's 0. Okay. I always want to keep on signing this caution that horizontal forces are not by default 0. Don't make it default. Anytime you see horizontal force 0 offer, if I come and grab your neck wherever you are. So now, checks. Okay? Sum of forces in the y is 0. Upward is positive. When it comes to calculation of reactions, I'm not expecting any other form of presentation from you. You must follow the presentation exactly. Okay? Don't use any other approach. Those approaches are not correct for me. There are a lot of shortfalls. So now, let me attempt to paste the diagram here. Okay? So this is the diagram. Is that right? So now, this one being the diagram for us now. What else? We have negative 55. I'm starting from the left. Plus VB. Minus 110. minus 110 plus VE minus 55. This should give us 0. So negative 55 plus 165 minus 110 minus 110 plus 165 minus 55. Check and see whether you get 0. I've also done the same mistake here. HB. Okay, thank you. I think that it has always been at the A, so my mind has also been programmed to follow suit. Okay, all right. So that's as simple as that. Okay, now I want to show you something. By the fact that we have what we call symmetric beam. For example, I can give you a beam like this in your CEM and ask you what is the value of the reaction. And I just want you to take about maximum 2-3 steps to get the answer, because that's a multiple choice question. So in that regard, I'm just going to use that opportunity to explain it simple here. If you have a beam symmetric beam, you can check whether the beam is symmetrical or not symmetrical. What do we mean? If we say the beam is symmetrical, simply divide the beam into 2 parts. I hope you are listening carefully. Compare the left-hand side to the right-hand side. If the loads are equal and their distances are equal, and you can say that everything at the left-hand side is equal to everything at the right-hand side, then the total reaction, okay, is simply equal to, you add all the loads and divide by 2. So this time, for example, if you look at this member, if the middle of the beam is somewhere here, okay, first of all, this beam has an overhang, 55. It has an overhang here, isn't it? It has another overhang. Are they the same length? Yes. So this one, overhang has passed. There's load at the end. The load here, 55. Is it the same thing? 55, yes, at the end. Then again, the reaction is located at 3 meters from the left. This is also 3 from the right, so yes. Then the load, after the symmetry here, the 110 load is at a distance of 3 meters from the support. This is also 3 meters from the support. So it means that if I draw a line in the middle, whatever at the left-hand side is equal to whatever at the right-hand side. If that is the case, then my reaction VB is equal to VE. Then it's equal to, just sum all the loads. So I have 55 plus 110 plus 110 plus 55. When you finish, divide it by 2 and you get that answer. So once it's symmetrical, it tells you the reactions are the same. So even without any rigorous calculation, you should be able to even know the answer for this particular problem. So this beam is symmetrical. Note that even if all the loads are the same and the distance of the forces, okay, and the distances of the forces vary, then that cannot be a symmetrical beam. Okay? When they vary from the center of the beam, it cannot be symmetrical. In the same way, if let's say there's only one overhang, clearly it cannot be a symmetrical beam. If let's say with the overhang here, this length is, let's say, 4 meters, whilst this one is 3, this beam does not qualify to be a symmetric beam. Okay, so symmetric beam means the reactions are equal. So once you detect that the beam is symmetric, if you want the reaction, sum all the forces and divide by the total number of vertical reaction, which is 2. Okay, this is very simple and very applicable to determinate beams. Okay, any question here? So take note of that. These are simple approaches you can use to evaluate your beams, okay, in a very, very simple and easy manner. Okay, so now we have finished solving that problem. So let's pick another, let me see whether there is another problem or not. We'll pick another problem here. Another problem. Good. So there's another problem. Problem 3.9. You have problem 3.9. Given. So we have a support here, and we also have a support here. Okay. Okay, so this load is 45 from here to here to here and to here. This is 3 meters, 3 meters, 8 meters. So this is a given. I want you to verify whether this beam is symmetrical or not symmetrical. Verify it. I want to have the answer. Is A, B, C, and D. Verify. Don't just say yes or no. Verify first. Okay. Leslie is saying it is. So I want others to also verify and provide their answers. Is it symmetrical or not symmetrical? Okay, a lot of answers are coming. I will check the answers very soon. Solution. So I'm going to draw my free body. So I have a vertical force here, and I also have horizontal force. I have HB, and this is VB. I have a vertical force here, and this one is the VC. Okay, let me see. A lot of answers have come. Okay, good. That's fine. I've seen a very Osai Emmanuel Hine has also provided a long justification. Matthias here, why? So if it is symmetrical, what should be the reaction? What will be the reaction? What will be reaction B and what will be reaction C? Okay, I've had one answer. Okay. So Humphrey, you are right. I am accepting the answer without unit, but note that the answer must always come with a unit. It's important. Okay? All right. So now, as we have learned, once you have a system like this, okay, it is better to convert, the whole thing is UDL, okay? The whole thing is UDL. Since the whole thing from the beginning of the beam to the end is the same value of UDL, we'll convert everything together like this. It will fall somewhere here, and this one will be what? 45 times the entire distance covered, which will be 14. Okay? 3 plus 3, 6 plus 8 is 14. And this will act in the middle. So if it acts in the middle, it means that from here to here, okay, that will be half. Okay, so this will be 7 meters. If this is 7 meters, what do you think will be this from here to here? This will just be 4 meters. Okay, from here to here, 4 meters. So I can decide to write my 7 or ignore it, because once I have it relative to the support, that's fine. So this will also be 4 meters. Okay. I hope this is good enough. Okay, so I'll clean the 7 here. Good. So now let's proceed. So taking, sorry, let me indicate that this is my free body diagram. So taking moment about B, that's what the reaction is. So sum of moment about B is equal to 0. Anti-clockwise is positive. So this time out we have VB. We are taking moment about B, so these two forces will be 0. We have 45 times 14. That is the force. And the distance to the B will be what? 4. In a square bracket. Minus, this is clockwise, negative. So plus this distance, the VC, times a distance of what? 8. Which is equal to 0, isn't it? So we have negative 2, 520 plus 8 VC is equal to 0. So that negative 52520, we have 8 VC is now equal to 2520. Okay, let me move out a little bit so that VC is equal to 2520 over 8. So VC is equal to 315. Okay, then we go to taking moment about what? C, okay? Sum of moments about C is equal to 0. Anti-clockwise is positive. So if we are taking moment about C, as you can see here, the VC here will have a distance of 0. Now we have converted all the UDL. So this will be anti-clockwise, 45 times 14 times the distance 4. And then the VB will be times a distance of 8, which will be clockwise. And then we are through, then the HB, okay? So we're gonna have 45 times 14. and this is the force, and the distance will be 4 in a square bracket. This will be anti-clockwise, so it's positive. Then minus what? VA times 8. Okay? Then plus HB times 0 is equal to 0. So this will give us 2520 minus 8 VA. Hey, I'm doing the same mistake. It's not VA. It's not easy. VB plus 0 is equal to 0. So that when we add all that, we'll get 2520 minus 8 VB is equal to 0. So that negative 8 VB is equal to negative 2520. So here VB will give us negative 2520 over 8. And VB is equal to 315 kilonewton. Do we have horizontal force? Yes. Okay, so I see people working behind the scenes. I see Mensa and Nati, including Humphrey. Okay, so I don't want to be going back and forth again. So horizontal forces. Sum of horizontal forces. So we have sum of forces in the x direction. 0 right way is positive. We have only 1, so at B is 0. We apply the checks. Sum of forces in the y, 0. Upward force is plus. Okay? So with that, we have the VB, right? I don't want to go back there. We have the VB minus 45 times 14, plus DC. This should give us 0. So this is 315 minus 630 plus 315. When we evaluate this, we'll get 0. So check. That's all. So we are left with one more example, then we'll be done for the day. With all this, a lot of work I'm doing, the aim is to help you understand, to be able to solve reaction for any form of beam you come across. That is why I'm spending a lot of time doing these calculations. Okay. So now, any question? Any question? So from here, we want to look at the last, maybe that one may not solve to the end, I can't tell. We want to look at the last scenario called beam with internal hinges. That is the last thing we are going to look at. How to analyze such beams. So beam with internal hinges. I know you have seen some of these before. It's not new. Okay? So before we even take any whatever, so we are talking about if you have a beam, let's say like this, and let's say you have a force like this, okay, and there's internal hinge here, there's hinge. What do you do? Hints. Number one, draw the free body diagram of the entire beam. Number one, draw the free body diagram of the entire beam. That's the first thing to do. Number two, separate the beam segments. The beam segments into other parts at the internal hinges. At the internal hinges. Number three, analyze each segment as a separate beam. As a separate beam, and apply the necessary checks. Okay, now let me remove this thing from here before it gets somebody entirely confused. Then number four, apply overall check for the entire beam. Apply overall check for the entire beam. Number five, if the checks for the separate segments. And the overall checks are satisfied your analysis is correct. Okay. So what I just want to add here is hence. Okay. A. J. Henry, your observation is not correct, right? Your observation is not correct. If you have a negative number and you divide by another negative number, won't you get positive? Won't you get positive? So there's no Dariga mathematics here. They are all mathematics. We have obeyed the mathematical law from beginning till now. So there's nothing like doing no. You must obey the mathematical rules. There's no gymnastic like if you divide by a negative, you ignore the negative. There's nothing like that. There's nothing like that. This is basic mathematics. So I don't want to talk much about that. It's just mathematics. Okay. Now, so just for illustration purposes, if you have a beam with internal hinge, for example, let's consider a beam like this. So let's say this side, is a fixed support. And let's say this side is a roller support. Okay. And let's say that we have forces here. Let's say we have some UDO here. I'm just illustrating, okay? It's just an illustration. And let's see, we have a hinge here. We have a hinge. Let's say we have a force here. Okay. Let's say we have P1. We have omega per meter here. Okay. Let's say we have A, and let's say we have B. We have C. We have D. So when you have a beam like this, remember that the hinge divides the beam into several parts. So if you have one hinge, you have two parts. If you have two internal hinges, it means the beam must be divided into three parts. So on and on and on. So like here, the first thing I expect anybody to do is to draw the free body. Okay? So right now, that's the free body I'm attempting to draw. So this part is a fixed support, so vertical, horizontal, and a moment. Okay, so this will be MA, HA, VA. Okay, and this side would be it's a roller, so this will be VB. So this original beam, this is a free body diagram. So do you see the step? So we have the original beam. We have the free body. Yes. So after that is not finished. You now have to draw the beam, separate the beam, draw the beam separate the beam. So this is how I'm going to separate the beam. So that is the first one is draw the free body diagram. The next one is separate the beam at the hinges. Okay? So if I'm separating the beam, I'll take one part and draw it, and take the other part also and draw it. So let's see how I'm going to just separate the beam at the hinge. So like this. Okay, I'm going to separate it like this. So you see that it's the same thing. Now what am I going to do? I'm going to separate it. Okay, let me just use some small wisdom here. I'll use this wisdom here to deal with the beam in a very, very interesting way. If you have wisdom, it's nice. It's very good to have wisdom, right? So those who lack wisdom, they say that ask God, God will give you wisdom, plenty. I believe people are watching keenly. Monhwɛ nea meyɛ no. Okay. Ideally, I was supposed to delete this one. Do you get it? Good. So separate the beam at the hinges. That's what you are seeing me gymnastically doing here. So I'll move up a little bit. Okay. So now, once I've separated, I need to get rid of this so-called hinge here. I need to get rid of it. Okay? Because now I've separated it. So it's like this. Okay, I started from here. Okay? So at the hinge point is here. This side to the hinge point is here. So what do I do? After separating it, you notice that the beam looks as if it's hanging, right? So after separating it, introduce two reactions. Listen carefully. After separating it, introduce two reactions at the hinge point. So if I take one to be up like this and another one to the right, okay? Or I can take it the left side, one to the right upward and to the one to the left. So from here, I come back to this, the next portion in the same point. Now I will use the reverse the direction of the forces. This must be obeyed. Reverse the direction of the new reactions you have introduced. Okay. Reverse the directions. So this time around, this is point D. Okay, this is point D. So I have H, D, I have V, D. Take the same reaction here, but reverse the direction. So this one will be V, D, and this will be H, D. Okay? So apparently, if you have done it like this particular one is part. Okay? This one is part. This part AD. Okay? And this particular side is now part. What do you call it? DB. I think I should avoid using the blue so that we know the blue has been used for a specific purpose. Okay, so this is part AD, and this is now part DB. Okay, note that the beam will always have distances, and the distances must be provided. The distance man. So all that I've done here is number one, redraw the free body diagram for the entire beam. Okay, so this one is segments. Or the parts. Okay, because there's only one internal hinge, you have two segments. You have two segments. So just Those sending their name, I don't know what exactly what they mean. Okay. I don't know exactly what they mean. This time I will not tolerate some of this nonsense. So be careful. Now, so you have the original beam. Redraw the original beam into free body diagram. Complete beam. When you finish, draw the separate parts of the beam by separating it at the hinges locations. And in that case, wherever you have internal hinge, you must provide vertical and horizontal reaction at each hinge joint. And the same joint, remember, the reactions that you provide for the left side must be equal but opposite to the right side. Okay? So if somebody had made this side to go to the right, this should have gone to the left. If this were to go down, this should have gone up. And this must be obeyed. This must be obeyed. Okay? All right. Any question here? Then I will attempt to, either I will leave it for you entirely to go and deal with it, or I will attempt to solve one problem with that and then. Any question? Any question? Any question? Okay, so now I will just provide a question here. I'll just provide a question here. So problem 3.10, because it's already in the slide, and I'm not going to waste too much time. Problem 3.10. So this particular problem this time around is going to be, it's like this. This side is a roller support. And there is an internal hinge somewhere here. Internal hinge here. Then I have a UDL here. Does this look like a UDL? Okay. Then I have a point load here. This side is fixed. Okay, this is 21.9. This is 1 3 kilonewton. And this from here to here to here to here. This is 6.1 meters. $10. All right, so this is the problem we have. Let's simply break it down and then we'll leave it. I'll leave the solution for you to go and solve it. So this is given. Given. Solution. Okay. Let me listen to Elias. Elias. Yes. Yes.
I want to ask you when they take in the question in terms of the differences, whether they will be given millimeters.
I'm coming. This thing is not clear. It's very blurry. Can you put it in a message box? Because it's very difficult to hear you. Hmm? Okay. So this one, I'm just going to draw the separate parts and then I'll leave the rest for you to go and do since you know how to do it already. Copy. Nkwana, Professor disturb me. Okay, so this part now is a free body diagram, which I want to draw. I'm attempting to draw. Okay, this side is a, oh, let me see whether there's some labels. This side is a hinge. So this is A, B. Let's call this place C and call this D. A. So this will be VA. B. Oh no. This side is the hinge. And this is C. This is D. This side is the fixed end. Like I told you, you can show the arrows in whichever form you want. Okay? So this will be HB. This is the moment MB. And this will be VB. Okay, so this is a free body diagram. Okay? So this being the free body diagram, as I said, now you draw the separate parts. Okay, you draw the separate parts. Okay, so now what I'm going to do is I'll just drop the right answer. I'll just drop that one. So I'm just going to do a small modification here. You should know that your approach should be different from mine, the way you struggle to, because me, I am kind of teaching here. Let this go up a little for me. So I'm going to drop this side. Okay. Let me drop it, drop it. Let me drop it like this. Good. So now that I've successfully dropped it like this. So this is the first internal hinge point. Okay. So I'll draw vertical. Okay. Vertical force and a horizontal force. Or if this force, I draw it like this. Okay. Or whichever way, if I should draw it like this. Okay. Then this particular one here must move to the right, and then the vertical one must look downwards. Let me clean something here. Okay, so now this is point C. So this will be H, C, and then this will be V, C. This again is VC, right? And this one is what? HC. So as you can see, they are equal but opposite. Okay, that's all you should know. So this is actually point C. This is also point C. So this one now, so you can just say this is segments or parts. So this one, this is A to C. You can call it part. AC. And then you can call this one part. C, CB. Okay. All right. So this is what is expected of you. So right now you take each of the parts, you analyze it as if it's a separate beam you have ever seen. So let me attempt to move This one a little above. It looked too close for me. Okay, so I'll just drop this one to a little high. All right, so that's all. So you have done the free body diagram. This is the free body diagram. Okay, so what I expect you to do here is, now that you have done this, you now proceed with the analysis. Okay, so first of all, leave the free body diagram first, leave it. Pick this part. You need to make sure that the part you have taken, the first one you are solving, will help you to be able to calculate the reaction easily. So if you look at the left, the part AC and part CB, maybe if you deal with the part AC first, it will be helpful. Whichever part you deal with is still okay. You can just, but you may end up having two unknowns and you have to leave the equation and go to the other part and go and solve and come and substitute. But if you look at the simplest part first, that will become very helpful. So in this case, the part I will start with the part AC. Do you get it? I would have started with the part AC. I think something has dropped here. Okay. Per meter. Okay, so you now take part AC and then you do the same things. Sum of moment about A is equal to 0, sum of moment about B, C is equal to 0, sum of vertical forces, and then sum of horizontal forces, and then you check. If that is correct, then you now move to part synchra. You now move to part CD. Okay? Now with that part CD to a similar thing. You do it like the way we have solved all the previous beam, in a similar manner. Whatever reactions you get from the other side, you may have to transfer the values onto the other part. So, and here, there's some caution here, okay? There's some caution here. I know some people will do it and get this thing all right, and they'll begin to change things. No, I'm coming. Part C, B. So let's say that if I calculated this part AC and I got reaction HC to be equal to -10 kilonewton. When you are doing substitution, don't go and substitute +10. Just substitute the exact value. Is that right? And substitute the exact value. So I think that when you now finish everything, there is what I'm calling the overall check, which means now come to the free body diagram here and use sum of forces in the y direction. Okay, sum of forces in the y direction is equal to 0. On this free body diagram, the entire beam now, and check. If your answer is 0, then it means you are completely correct. You can put in your name and index number. However, if there's any question, please ask so that I can address such questions now. Any question? Okay. So if you don't have any question, then I want to thank you for participating in today's class, and also a reminder to all those with the assignment. This time around, if I find that you don't come to class, I'm going to engage you. And remember, if you don't meet the minimum of 70% attendance, you have no business entering into the exam hall this time around. You'll be sacked from the exam hall. You will come and write the paper as a receipt. So take note. You'll be sacked from the exam hall. You must meet minimum of 70% attendance to be able to participate in the exam. Okay. Now, let me take a question from Elias. Elias, can you speak up? Okay. So let me just ask a few people, just maybe two people. What's your impression about today's class? Okay, Manaf, I will do that shortly. What's your impression about today's class? Okay, I think I've seen a hand. Yes.
Hello.
Elias, speak, I'm listening. Okay, Seth.
Yes, sir.
Seth, hold on, let me
So
mute.
I was getting
Okay.
everything onto the last part.
Seth, unmute again. Okay. Come again.
Okay. Good morning, sir.
Yeah, good morning.
Good morning, sir. Thank you for the lecture. Please, I was understanding everything onto the last part when it comes to the calculations.
Which one is the last part?
That's just this one, the one on the screen.
Yes. This one, we have not done the calculation. You are going to do it.
No, I mean the explanation you gave about how to do the calculations, I didn't really get it.
Okay, the video will be available. You can listen again and again. Okay.
Okay, sir.
All right.
Thank you.
Okay. All right. So thank you all for your time. And so we ended the class in the name of God the Father, of the Son, and of the Holy Spirit. Amen.